Welcome back to the hyperbolic coding chamber. Looking kind of drippy today. I got a special haircut. Today is day 20 of the daily LeetCode grind. Yesterday I got fried by merge intervals, but I fried some easier problems. Now that I'm thinking about it, missing ranges and merge intervals are probably similar. But yeah, I got fried by this problem. We read the solution, so we should be able to get some intuition. So we'll try this one again. I'm learning that LC mediums is no joke. LC hard's probably impossible. Courtesy of the Copy Ninja. Got some comments. So yesterday's video said avoid LC 53 at all costs, but you never do problem 53. Actually true. The actual problem was LC 56, which was merge intervals. So I'm kind of cringe. I went back, edited the video. So shout out to the Copy Ninja. Also, you have Blake who said promosum. But excellent comment nonetheless. Yeah, for the problems due today of +1, which is actually tangentially similar to add two numbers, except you only add one instead of adding two numbers with the carry and so on. Then we have missing number, and then I'm thinking we'll do a random weighted problem, and then we'll try merge intervals. But this time I'm actually gonna stop after 20 minutes, so maybe I'll have another timer that I'll set with the clock app. I've returned, so we'll probably have two timers here. We'll have a 20-minute one and a 1 hour and 30 minute, which will be the entire session, and then 20 minutes will be per each problem, just because I don't know how valuable it is for me to spend an hour struggling on a problem. But there needs to be a struggle timer, so that's what the struggle timer will be. So each problem I'll set 20 minutes, and I think this should be a good way to keep working on the problem. Other reflections, another mistake I made was I did merge interval yesterday, and 2 days ago I did LRU cache. I haven't retried LRU cache, so I need to implement a blocking mechanism sort of. So if I get stuck on merge intervals, I'll do it every day until I get it, and then I'll do LRU cache until I get it, and so on and so forth. That way I can keep a pool of problems that I'm struggling with, but not spending all my time on one problem. That being said, struggling helps to retain the issues. So I think struggle is another means for elaborative encoding. So the longer I struggle on a problem, when I do figure it out by reading a solution, it should help. So that is the goal. And the 1 hour and 30 minute session should help as well. But those are the main problems I think so far. You should also join the Hyperbolic Coding Chamber Discord. Very jumping Discord. It's a party. And majority element and missing ranges I haven't done yet. And we're still working down this list here. So it's pretty much the top interview questions. And then maybe we'll try top Amazon or maybe top Google. The end goal would be to do all the problems or have them all have done at least every problem once. I'm hoping that leads to a gain of skill. I read a book called Ultra Learning, and it's a similar mechanism. It's kind of like, since you don't really know what to do to become really good at something, if you set a ridiculously high bar, for example, doing all the LeetCode problems, you have to learn something along the way, right? Because you solved all 2,000 problems, so you have to know how to do something. So that's kind of what I'm aiming for. And then maybe I'll move on to something else after that. Maybe we'll do HackerRank or one of those programming question websites. Actually, probably move on to front end stuff. So that being said, I'm going to start with the usual problems. I'm going to start the 1 hour and 30 minute timer, and I'll start the 20-minute one as well. Start with +1. Go for this would be linear time and linear space in the worst case. So we have function plus 1, which takes a digits, which is a number, an array of numbers, returns an array of numbers. We're given a large integer represented as an integer array digits. Makes sense? Where each digit sub I is the ith digit of the integer. Digits are ordered from most significant to least significant, as opposed to least significant to most significant, like in add two numbers. The large integer does not contain any leading zeros. So we can increment the large integer by 1 and return the resulting array of digits. So what does it look like? So 1, this array of 1, 2, 3 is represented by, well, 1, 2, this array of 1, 2, 3 actually represents the integer 123. We'd like us to add 1 to it and then stop. And then we have 4, 3, 2, 1. We add 1 to it, then we stop. And they actually give us a little hint with this edge case. If we have 9, if we add 1 to it, right, we should get another number, right, which would be 1, 0. So they're adding a 1 to the front of the array. So the digits length can be up to 100, so we can't use regular integers. Symbols go from 0 to 9, so it's base 10. And digits does not contain any leading zeros. So one way you can do this is elementary addition, and it's similar to add two numbers in the sense that we want to iterate over digits in reverse, right? And if our number is greater than 9, right, then we're going to want, oh, we'll start with this. If our number is non-9, we'll just add 1 to it. If num will non-9, add 1, done, right? Because iterate in reverse will start at 3. If its number is non-9, we add 1 and return 4. Now when we have 1 to 9, if we iterate in reverse, if we add 9 to 0, I mean 1 to 9, we should get 10, right? Which means we have to carry a 1. If that's the case, right, on the next iteration, we'd add 1 to 2 and get 130. So what we can do, code-wise, is just turn all 9s into zeros to simulate the carry continuing. And then if we run into a non-9 number, like we set up here, we'll add 1 and we'll stop. So else turn num into 9, right? Edge case, right? So we're gonna have 9 here, right? If we have 9 here, right, iterate over digits in reverse, we start at 9. The number would be 9, so we, oops, I said turn num into 9. We turn the number into 0, so we'd have would be 0. Well, in that case, what do we want to do? So if we can exit through here by adding 1 and we're done, if we make it outside of our iteration, it means that we never met a non-9 number. If that's the case, then our array looks something like this. Another addition that could create this is 999. We turn all the zeros into 9, right? And then we'd get to our outer loop and we'd have 0, 0, 0. So in all these cases, what we see is that we need to add 1 to the front. And then we can return digits. So we can iterate, we can implement this. So we do I is equal to digits.length minus 1, right? So we're going to start the last element in the array and go until I is greater than or equal to 0, I minus minus. And then we'll say if num sub I does not equal 9, right? Then we said that we would add 1 to the number. So we'll just say, I said nums should be digits. So digits sub I equals digits sub I plus 1. And we can return digits. So they wanted us to return that value once we were finished. In the else case, right, we said we turn digits sub I equal to 0. Now here we're going to want to add a 1 to the front and return digits. Let's delete the pseudocode. So this looks good. The time complexity would be linear time, and the average space complexity would actually be constant space. We have an edge case, right, where if the number is all 9s in the worst case, right, we turn all the zeros into all the 9s into zeros, and we have to add a 1 to the front, in which case we technically would be allocating up to n digits of space, so we'd say linear space. So I'll reset this timer. We'll do missing number. So we have function missing number. We have an array of numbers, and we have to return a number. Given an array of nums containing n distinct numbers in the range 0 through n, return the only number in the range that is missing from the array. So we're given an array of nums, all of them are distinct. We have to return the numbers in the range containing n distinct numbers in the range 0 through n. Return the only number in the range that is missing from the array. This problem statement's a little confusing, but let's just look at the input and outputs. So if 3, 0, 1, this would be the range 0 to 3 inclusive. Number that's missing is 2. N equals 3, since there are 3 numbers. All numbers are in the range 0 through 3. 2 is the missing number. Okay, so then we have nums equals 0, 1. The range is 2, 0 through 2 inclusive. Number missing is 2. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And the number missing is 8. So it looks like the array's length shows the actual range. So there's 3 numbers in the array. There should actually be 4. I mean, there's 3 numbers in the array, so n is actually equal to the nums.length. And if there's 0 through n numbers, there should be 4 numbers, including 0. So one way we could do this is we could sum all nums in nums and subtract the actual sum of the range of 0 through n inclusive. So to get the sum, we could use a reduce function with a and b, and we could do a plus b to get the sum of the numbers in nums. But then we actually need to get the actual sum of the range, and then we can subtract abs. Get the absolute value of the difference. Because if we know that the range of n distinct numbers should be through 0 through n, if we sum all these numbers, it should equal a specific amount. So let's just say for the range 3, we have 0 plus 1 plus 2 plus 3 equals 6. But here we have 3 plus 0 plus 1 equals 4. So 6, which is the actual sum of the series, minus 4, which is the actual sum of nums, gives us 2. And this should be 2, so we should have, the sum should be 3. And if we do the sum, we'll have 3 minus 1, which is equals 2. And I'm sure we'd have the same at the bottom here. So we can calculate the sum of the series in constant time with the Gauss formula. So that would be n times n plus 1. Dot length times n times n plus 1 over 2, and we can return sum minus Gauss. So let's check it for this one. Our range is 3. It'd be 3 times 3 plus 1, which would be 4. 3 times 4 is 12, over 2 would be 6. So that looks good. So that looks good. Looks like linear time to calculate the sum, and we can't do any better than linear time. for the sum, because there's just no way to know what numbers are included or not included. So we just have to sum them all. And then Gauss is be constant time. We have binary tree, in order traversal. So we'll restart this 20-minute timer. Given the root of a binary tree, return the in-order traversal of its values. So in-order traversal usually refers to depth-first search among the relative ordering of the nodes, which would be L, N, R, where in-order means that N is in the center. So we have the root of a binary tree, and they'd like us to return the in-order traversal of its nodes' values by returning an array of numbers. So this tree is 1, 2, 3, 1, null, 2, 3. So our binary tree is actually represented as an array here. And our output should be 1, 3, 2. So L and R would look like, we start with 1, which is the root. We'd go to L, should be null, then we'd go back to N, which would be 1, then we'd go to R, which would be 2, and from 2 we'd go to L, which would be 3, then we'd go to left of 3, which would be null, then N, which prints 3, then R of 3, which is null. Pop that call off the stack, we'd go back to 2, which would do N, which would print 2, R, which would be null. We pop that, and we would be done. So we can probably do this with recursion, where we will number of nodes and trees up to 100. So we have this array of numbers that we want to return, right? And we could pass in the root with nums and then return nums. So this recursive version and we don't have to worry about handling when root is null, since we just return an empty array. We'll pass in nums, which is going to be an array of numbers, so that we can modify nums, the reference to nums, by reference. First thing we want to do is check if the node exists. And if it does, we're going to call helper again, except with node.left, and then pass in nums. And then we're going to do n like we said, which is going to push node.value. And we can do node.write nums. So this looks like linear time, since we'll have to visit every single node in the binary tree to create this array of numbers. So it'd be linear time, where n is the number of elements in the number of nodes in the binary tree. In the worst case, our space would be linear time as well, since we have to visit every node. Each visit of every node is technically a call, technically a recursive call, which would use space. So it'd be linear space as well. That checks out. So we'll try follow-up. Recursive solution is trivial. Could you do it iteratively? So we could do it iteratively, except we would need a stack to assist us for in-order traversal, and we'd also need the array of numbers. And so what our goal would be here is that we'd use the stack to simulate the recursive nature of calls, because when we do a recursive call, we're technically pushing, the function's resources onto a stack that get layered on like plates. And recursion works the way it does, because once this plate is done, we pop this off, and this one, then this one, then this one, this one, all bubbling back down to the first call. So the way this would look is we would say we would need a node, right, to preserve the root. Say, well, cur does not equal null, or the stack isn't empty, right, we're going to have a block of code where we're going to force our collect as many nodes as we can to revisit while going as far left as we can. So cur does not equal null. We would do stack dot push cur, and we do cur equals cur dot left. So if we think about that, if we pass in cur, which would be root, we'd start at 1. 1 wouldn't be null, the stack doesn't matter because we're short circuiting. And then 1 isn't null, we push 1 onto the stack and then go left to null. Right, once we've gone left to null, right, cur is equal to null. So now we're going to be out here. What do we want to do when that happens? Well, we want to do the end part, right? So what we would do is we'd say nums.push cur.val. And so now that we're here, what do we want to do next? Oh, no. We wouldn't push cur.val. First, we would say cur equals stack.pop, right? Because cur would be null since we're at cur.left, which would be 1.left, which would be null. We'd be null here, so you want to set cur equal to stack.pop, which would be 1. Now we want to push 1, right? So this is the processing step. Then we'd want to go right, because it's L and R. So we would do cur equals cur.right. Then we go back to the top, and our right would be 2, right? So it wouldn't be null, but the stack would be empty, but we short circuit, so we don't care. Then we want to go as left as possible before we start doing the same thing again, right? So we'd push 2 onto the stack, then go left to 3, push 3 onto the stack, then go left. We'd be null, so we'd pop 3 back onto cur, and we'd push 3, right? Then we go cur.right. Well, right is null, right? Go up here, cur would be null, but the stack wouldn't be empty. Cur is still null, so we do stack.pop again. We get 2. We'd push 2 onto the array, then go right for 2, but 2 would be null, and then we'd go back to the top. 2.right is null, and the stack is empty. Then we could return nums. So that looks good. So now we'll reset the timer, and I'll try. I think we just did +1. I'll close that. I'll try merge intervals again. So we have a function merge with intervals. We have an array of numbers. We have an array of where the inner values is an array of numbers. So we basically have a matrix, I guess. And given an array where interval sub I is equal to start sub I and end sub I, merge all overlapping intervals and return an array of the non-overlapping intervals. That cover all the intervals of input. This sentence makes no sense to me, but what it looks like is that when there are intervals 1, 3, and 2, 6, they overlap, so we should merge them to 1, 6. Since 8, 10 doesn't overlap with 15, 18, we return 8, 10, and also 15, 18. Constraint that the intervals always has at least one element in it. In intervals, I always has at least 2, or a tuple, interval tuple always has at least 2 elements in it, and there's at least one interval in the intervals array. And start can go from 0 all the way up until 10 to the 4, including end. But start is always less than 0. It's always less than end. So my original solution tried to do a double while so that we could process the intervals in a pairwise fashion, but unknowingly it had the requirement that the interval array be sorted by the first number in the interval. So that could be added now. That could be added now. Either way, we have output dot this solution. I'm not sure if I want to try and retry it again or just try with what we learned yesterday. What we learned yesterday is very similar. You can just say sorted equals, actually I think this interval sort in JavaScript actually sorts it in place. Intervals dot sort t1 and t2 would be the tuples. We'll just say type tuple interval equals a tuple of two numbers. We actually don't even get any type information for this, so it doesn't even matter. We want t1 sub 0 so in ascending order, so we have t1 sub t2 sub 0. So you'd already be bound by n log n. We have let s1 equals intervals sub 0, 0, and let e1 equals interval 0 sub 1. So what if we just did it by hand again? We'd say iterate over the array, and we'd say is 3 greater than 2 and less than 6? Yes. If that's the case, then we would turn n interval to 6 and we'd keep going. Go to the next iteration. Is 6 in the range? No. Then from there we'd add 1, 6. And where we currently are. So maybe we don't actually need an inner while loop. Maybe this could be an if. So if 3 is greater than 2 but less than 6, we do E2 equals, or E1 equals E2, right? And then else, we would subtract that, we do I plus 1, we go to 8. If 8 doesn't pass it, then we could push output.push S1 and E1, so we get 1, 6 on the output. Then maybe we would set these to the new values that don't and overlap. And we go to 15, 18, see if they overlap. And they don't, so we push A10. Then at the end, we could check one last time. So you could check one last time. We'd say if if 10 is greater than 15 and less than 18. Basically, you want 15, 18 at the end of the array. So you start at 1. E1 would be 1 and 3. S2 would be interval sub I. I is less than the length. We probably don't need that anymore. We'd say if 3 is greater than 2 but less than 6, or if 2 is greater than or if 3 is greater than 2, then N2 equals E2. Okay, then we do I plus 1, we'd now be at 8, 10. 6 would not be greater than 8 and less than 10, so we'd push 1, 6 onto the array. Then S1 and S2 would become 8 and 10. We'd increment. 8 and 10 wouldn't overlap 15, 18, so we'd add 8 and 10. And then from there, we'd add 8 and 10. And then from there, I would equal 4. I would equal 4. If I equals 4, then we have to check one last time. S1 and E1. We want 15 and 18 at the end. You can't just push it at the end. I need to track where I is. I'm getting confused. Start at 1. We'd go to 2. We'd push 2, 6. Now we'd be 8, 10. We'd go to 3. We'd push 8, 10. Then we'd go to 4. 4 is not less than 4. So since 4 is not less than 4, four is not less than 4. So we could say if we pull these values out of intervals dot length -1 and S1 equals S2 and E1 equals E2, then we just want to push S1 and E1. No way. Aww. So it looks like 1, 4, 4, 5. So E1, S1 will be 1 and 4. So this actually looks like a, if E1 is greater than S2, I think this has to be equal. Because 4 is equal to 4, so they'd like us to keep that value. Since that's the case, I would run E1 equals E2. Oh, it would actually end right there. So you'd never have pushed anything onto the array. So still another problem because you wouldn't have pushed anything onto the array. But if they equal each other, they wouldn't equal each other. So another thing we could do is try to figure out this off by 1 thing. What if we just started I equals 0? That way, B1, 4. It would be fine, and then they would match on the next iteration. We still wouldn't do anything because we only push when they don't match. So it looks like the best way to do it, maybe how they originally did it in the problem. This is possible. Maybe we could sort them like they said, and then from here we could have output could equal an array, and we could iterate for num of intervals and then from here we could say if output dot length equals 0, then we want to just push the empty interval onto the track, and then we'll just work backwards. We'll start we'll work backwards. So we'd say output dot push the interval. Otherwise, right, we want to make sure that be prev s and prev e will be prev start and prev end. We'll do intervals. Maybe we'll do an I equals 0, I is less than intervals. Actually, no, we can still do numbers. We want to work in reverse. And so the last thing what we're working in reverse is actually the output. So we would say output, so output dot length minus 1. So output length is 0, we're just going to push the interval on. Otherwise, we're going to check if E1 is greater than or equal to prev s and E1 is less than or equal to prev e. Or we could do if E1 is greater than or equal to prev s. In that case, we'd want to merge them. And the reason this works is because what we're merging. Actually, we want to reverse these. We want to do prev s is greater than s1 and prev e is less than or equal to e1, and prev e is greater than or equal to s1. Then we can simply change output dot length minus 1 sub 1 would equal e1 to merge the range. But when do we push? Else maybe we push the interval. So to test that, we could do 1, 4. We sort it, right? So we'd have them just as they are now. We'd iterate over the intervals. So we'd push, we'd pull S1 and E1 out of the current interval, which would be 1, 4. But output.length is equal to 0, so we'd push 1, 4 onto the output. Go to the next iteration, we'd pull 4 and 5 out of the interval, and prev S and prev E would exist. So we do output.length minus 1. So we have 4 and 5. Output.length isn't empty. So let's check if prev E, which would be 4, is greater than or equal to 4. It is, and it's less than or equal to 5. So we'd say output.length minus 1 sub 1 would be equal to E1. So that makes sense. And let's check it for this one. We'd have 1, 3, 2, 6. So we know we'd push it's already on, so we actually don't have to do anything. So now we'd have 1, 3, and 2, 6. So we'd modify the original interval to 2, 6. Then we'd have 8, 10 on the next iteration. We'd pull 8 and 10 out. Then we'd have 1 and 6 on the previous pulled out. Output isn't empty. And we check if 6 is greater than 8 and 10. It's not. So we just push the current interval on, 8 and 10. We'd pull the last one out again. Between 15 and 18, is 10 greater than 15, less than 18? No, so we'd push the interval, then we could return the output. And I think this looks good. Never mind. Output.length minus 1. Undefined is not iterable. Undefined is not iterable. Undefined is not iterable. output.length minus 1. That doesn't make sense. Output undefined is not iterable. So for some reason output is undefined, output is equal to an array. Maybe you can't safe navigate. You definitely can safe navigate an array subscript. Maybe you can't destructure it. Let's try making this prev s and prev e, but like this. So you can't destructure something that does not exist. Interesting. So a small problem. If we sort this by the start, our output is 1, 3. So it looks like this or prev e is greater than or equal to s1. Maybe we remove that. So now my output is 1, 4 and 2, 3. What I want to return is 1, 4. So I'm pushing on, let's see what's happening here. I'm pushing on 1, 4 to start. My time is out, but I'm so close. I'm pushing out 1, 4 to start. If prev e is greater than s1, which it is, and prev e is less than or equal to e1, which it's not, we push the interval on. But it expected 1, 4. Why does it expect 1, 4? Oh, we shouldn't include, maybe that's what they meant in the original problem description. Return an array of the non-overlapping intervals that cover all intervals of the input. They don't want us to include ranges that. So it looks like we could also have else if prev e is greater than or equal to s1 and prev e is greater than or equal to e1, continue. feel like continue is always a sign that you need a better case. Okay, let me stop. This looks good. The solution, kind of ghetto. I'm pretty sure that there's probably a better way to do this. But let me digest the solution here. So what we did was we make the assumption that if we sort them all by when the interval starts, the overlaps will be easier to find. Or if it overlaps, it should be the next one. Right? Which makes sense because if we sort 1, 3, and 2, 6, and they end up next to each other, 3 just has to be greater than 2 and less than the end where 2 starts. This one's talking about a graph. I'm not even going to try to understand this. It's also got so much code. If we sort the intervals by their start value, then set each of intervals that can be merged. Sort the intervals by their start value, then each set of intervals that can be merged will appear as a contiguous run in the sorted list. That's a better way to put it. First, we sort the list as described. Then we insert the first interval into our merged list and continue considering each interval in turn as follows. The current interval begins after the previous interval ends. If the current interval begins after the previous interval ends. If the current interval, let's just say, is 2, 6, begins after the previous interval ends, which is 1, 3, then they do not overlap. That doesn't make sense because 2, 6 and 1, 3 do overlap. The current interval begins. The current interval begins, which would be 2, after the previous interval ends, which would be 3. If the start of the current is greater than the last of the end, then they do not overlap. That makes sense because 3 has to be between the two. So if 8 ends, so if the current interval begins, which would be 8, after the previous interval ends, which would be 6, and they can't overlap. And we merge them by updating the end of the previous interval if it is less than the end of the current interval. Simple proof by contradiction shows this algorithm always produces the correct answer. First, comma, suppose that the algorithm at some point fails to merge two intervals that should be merged. This would imply that there exists some triple of indices I, j, and k in a list of intervals ints such that I can be merged, neither I, j. To be honest, I don't understand the proof. Therefore, all mergeable intervals must occur in a contiguous run of the sorted list. Therefore, all mergeable intervals must occur in a contiguous run of the sorted list. I still prefer my original solution, even though it had some pretty obvious shortcomings. But that's the solution that comes more easily to me. And I think there's something to be said about that, because I think you want a solution that works more with how you think, since the way that you do the problem, I feel like it leaves kind of a signature of how you think. It's just easier to absorb. For example, I'm reading this one, it doesn't make that much sense to me, but I feel like the one I originally wrote is still fresh in my mind. I understand it. So it's kind of like I know this one works, this is why I'm writing it, but I feel like my original solution made more sense and you just handled the edge cases. But maybe mine could be fixed by actually adding this bit of code. Maybe they're not that far. Maybe they're the same. Mine is if prev e is greater than we would update it. Problem with that. So honestly, this one works a little bit, but we'll still do it again tomorrow because I don't think I still really understand it. There's no follow-up. Let me read the code. Merge, we have the intervals. This is Python. List of integers. We sort it by the starting interval. We have an empty output matrix. Then for every interval in intervals, if the list of merged intervals is empty or if the current interval does not overlap with the previous, so I think what they're saying is they're fusing mine. If the list of merged intervals is empty, or if the current interval does not overlap with the previous, then they push. Or if the current interval does not overlap with the previous, how can you check? You can check that by checking if E1 starts, if E1 is greater than prev E. S1. If the start of the current one starts after the last one ends, then they can't overlap. It needs to start before the last one ended. So S1 would have to be less than prev E. In that case, S1 is greater than prev E, then they append, so you don't need this case. Else there would be overlap, so we would modify the previous interval. I'm not saying what the problem is. Semicolon was expected. Add car 45 on line 11. Or S1 is greater than prev E. Otherwise, we pushed. Else. Oh. That's an interesting one. Gonna have, oh. This one fails on the same one that mine did. So they're taking the max of merge. So there's another case here. So you merge the current and previous intervals. They either take the max of, so we're technically always replacing the last interval. It's just whichever one is the biggest. Yeah, that doesn't make any sense to me. We have to do this one again. max of E1 and output sub output dot length minus 1 sub 1. Yeah, that just doesn't make much sense, so we'll probably do that one again another time. I'll do another weighted problem. So function Hamming weight, we have n colon number, which returns a number. Write a function that takes an unsigned integer and returns a number of 1 bits it has. The Hamming weight is a number of, in a unsigned integer, which means positive only, the number of 1 bits it has. Some languages such as Java, there is no unsigned integer type. In this case, input will be given as a signed integer type. It should not affect your implementation as the integer's internal binary representation is the same, whether it is signed or unsigned. Java, the compiler represents the signed integers using 2's complement notation. Therefore, in example 3, the input represents the signed integer -3. I think I see what they're saying. This would be 2's complement, so you flip it and add 1. So you subtract 1 and flip it. No, it has 31 1 bits. So if that's the case, we could do a masking type operation. So we could run this loop for 32 operations. Let ham equals 0, and then we can return ham, and then we could check if n, and do a bitwise and of 1. Actually, we could shorten this to ham plus equal n and 1, and then we could shift n to the right once. Now I don't know how integers are represented in how numbers are represented in JavaScript. I think they're always 64 bits, but maybe in this example our number will always just be maybe the number they give us will always just be the max of 32 bits. So that looks good. I would say this is linear time. It said if this function is called many times, how would you optimize it? We're just counting the number of 1 bits it has. Hamming weight, number of 1 bits it has. I don't see why this function would be called many times. And if you would, why would you optimize it? If you're calling it for an arbitrary number each time, you can't really optimize it, I feel like. Assuming that every binary number doesn't actually represent a number. Yeah, follow-up, I actually don't know how you would optimize this. Moves the least significant bit of this number. Check the next bit, we shift the mask. I remember this. In Java, they shift the mask by 1 instead of the number. For some reason, in JavaScript, this doesn't work. JavaScript doesn't work. You can make this previous algorithm a little simpler, a little faster. Instead of checking every bit of the number, we repeatedly flip the least significant 1 bit of the number to 0 and add 1 to the sum. soon as a number becomes 0, we know that it does not have any more 1 bits. Key idea here is that for any number n, doing a bitwise AND of n and n minus 1. Interesting. Bitwise AND of n and n minus 1 flips the least significant 1 bit in n to 0. Why? Consider the binary representation of n minus 1. Some zeros, least significant 1, rest of number. The binary representation, the least significant 1 bit in n, always corresponds to a 0 bit in n minus 1. Therefore, adding the two numbers n and n minus 1 always flips the least significant 1 bit in n to 0 and keeps all other bits the same. The least significant 1 bit in n. Runtime depends on the number of 1 bits in n. Worst case, all bits in n are 1 bits. In case of a 32-bit integer, the runtime is time, space complexity is constant space. Seems like you could speed this up, but it seems marginal. So it seems marginal. In the binary representation, so it looks like if you mask n, the least significant 1 bit in n always corresponds to a 0 bit in n minus 1. Therefore, adding the two numbers, ANDing the two numbers n and n minus 1 always flips the least significant 1 bit in n to 0 and keeps all. I see what they're saying. If you subtract 1, it turns the least significant 1 bit to 0. And if you AND them, you only ever run this operation the number of times their least significant bits, the number of time 1 exists in n. So to write this in JavaScript, we could do this as, well, n does not equal 0. We could do ham plus equal and ANDed by n minus 1. And we could say n equals n minus. I think n would equal n and n minus 1. Okay, expected 3. Okay, this makes sense. That's a cool way to do that one. think we can try LRU cache with the remaining time. Or maybe not. I'm not feeling that hype about LRU cache. Let's try number of islands. So we have function num islands. We have a grid with an array which stores an array of strings and returns a number. Given an m by n 2D binary grid, which represents a map of ones, land, and zeros, water, return the number of islands. An island is surrounded. Given an m by n 2D binary grid, which represents a map of ones, land, and zeros, water, return the number of islands. An island is surrounded by water, is formed by connecting adjacent lands horizontally or vertically. Given an m by n 2D grid, so we have this grid which represents a map of ones, land, and zeros, water, return the number of islands. An island is surrounded by water. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. We assume all four edges of the grid are all surrounded by water. There's one island. Here there should be 3 because we have 2, 1, but they can only be connected horizontally or vertically. Interesting. Given m by n 2D binary grid which represents a map of ones, land, and zeros, water, return the number of islands. Island is surrounded by water and is formed by connecting adjacent lands. So how could you make sure? I'm thinking maybe something with recursion here. We could do this one. If we start at 1 here, if we do a recursive function, and it would always check up, left, right, down. If up is out of bounds, then that's fine. We'd return the indice. This means that 1, 1, 1, 1, 1 I think we could do this with recursion and maybe a map. So we'd call 1. We'd call with the first indice here, and it would go check if this is a 1. It'd be fine. It would check if this is a 1. Okay. And then it would string all these indices together and say that these indices in any order are an island. Then we could iterate through the grid and ask to calculate each island for each one. That way we could know if we'd visited it already. So maybe we could keep a grid, so we could duplicate grid dimensions, iterate over grid, call find island. If grid, let's just say if grid sub I, so iterate over each over grid row, iterate over grid column, and we say if grid sub I equals 1, call find island. If we call find island, what it'll do is it'll say if I is equal, it'll check if the current index is equal to 1, and if it is, it'll set it to 0. Then it'll check if the right hand is equal to 1. Then it'll go and call right, or it'll call right. It'll check if the current value is equal to 1, which it is. It'll set this to 0. Let me copy it. So it's set this equal to, let's just say, x. Then it would go right. So you would always call up, left, down, right. Then it would call right, check if this is a 1. Actually, it's not how recursion would work. We call, check if it's a 1. And if it is, we'll turn x, then we'll go right. Check if it's a 1. If it is, we'll turn x, then we'll go right. Well, this is 0, so now we'll go down. We'll check if this is a 1, so we'll go, we'll change this to an x. Well, now we'll go, well, yeah, we'll go down, so this would be 1, we'll turn it to an x. Then we'd go right to 0, then we go down into 0, then we'd go left. We check if this is a 1, we change it to an x. Then we should go right. We know it already visited, so we'd ignore it. Go down. Nothing is out of bound here. This is already an x. So we'd know if it was an island if it returns 1. And then if it doesn't equal 1, then we just keep going, keep going, keep going, keep going. And then we could call for here. We check if this is a 1. It is, so we turn it to an x. Then we check right would be 0. Then we go down, left, up. We return 1. Keep going, keep going. So it looks like we could call find island. Then we'll have let islands equal 0. And we'll do island plus equal call find island. And I feel good about this one. I'll keep this up here. I'll have a function called find island, which takes the grid that we're going to modify, and it takes an x, which is a number, and a y, which is a number, and it returns a number. And so since this is the grid, it would be recursive. We would check, right, like we said, if grid sub x sub y equals 1, grid sub x sub y equals x. But first, you want to make sure that it's in the bounds. So you're going to say else if. So we'll say if grid, so x, if we want to check above. So actually, we'll stop. We'll do that. We'll do this one first. Change it to an x, and we want to check the right-hand side. Maybe this return, instead of a number, it returns a Boolean. So then what we want to return is grid x of y equals x. Then you want to say, or we could just say const I equals grid x to grid y. If value equals 1, else if value equals x. What do we want to do if it equals x? Maybe we'll just return false. Because we don't want to keep going. So maybe actually it's if value equals x, you want to stop. Or value equals 0, then we want to stop. And then out here, we actually want to do our recursive calls. And we want to return find island of grid, but we want to check above us. We also want to check, that's why we want to check above us to the right of us to below us, and we also want to check to the right of us. When do we return true? Else, if we return true, that doesn't make any sense. Because the bottom would never run. If we don't return true, but we say value equals 1, and we check all around us. That way, if value doesn't equal 1, then we'll just stop. If we iterate over row equals 0, row is less than grid length, row plus plus, call equals 0, and view call is less than grid sub row length call plus plus. I think this would be m by n, and so we would visit every element of m. We visit every element in the grid. We could just say if grid sub call sub row sub call equals 1, then we'll do islands plus equal find island grid row call, and then we can return island. So let's call this with grid equals this. So we're iterating over the rows, grid.length, and then we iterate over the columns would be grid row dot sub length. So if grid sub row should be 0 sub call, which should be 1 equals 1, we'll do islands plus equal find island. So we call find island with 1. Let's change all these x's to 1s. We call find island with 1, so grid sub x sub y would be 1. So it wouldn't be x or 0, so then we'd return the value equals 1, which it does, and find island grid of x plus 1. So we need to check out of bounds here. Should be or and. I think it should be or, because even if there's only 1, 1, these other calls just serve to make sure that we check all the connecting islands. So value equals 1, which does, and find island of grid sub x, which would be 0, plus y, 1. Row call. I think these would actually have to be swapped. Because the row, we actually want it in reverse. We want to check row would be 0. We want to check 1 above. The column would be here, so if you want to check 1 above, so call plus 1 would actually be checking would be the right hand side first. which is fine because the row sub call 0 sub 1, which would be 1, value equals x, or value equals 0. Actually, you don't have to check if the value equals 1 because we already know it does. What we want to do is set grid sub row sub call equal x. Then return true, or all these things together. So we call grid equals 1, and then we call find island. Wouldn't be x is 0, so we do grid sub row, which would be 0, 0 equal x. Then we return true, or find island of grid row comma call plus 1. Value wouldn't be x or 0, so we change this into x. Then we'd call row comma call plus 1, and it would be, you would change that one to x as well. And then here we call right again, we change this one into x as well. Then we change this one into, we go here, value equals x or 0, then we return false. Go back and check down, this would turn x. Then we check the right hand side, and it would be 0, so we return false. Then down, check down, and so we return false, and then left, then we go back up here, we check, it would already be, this one's hard to follow. So I want to print the grid after this and just do return just to see what it looks like. So after the first call of find, change grid row equals x and return true. Oh, I'm short circuiting. So we probably want to change this to or true at the end. Okay, so this looks much better. We remove the return. Okay, so this is good, and we'll say if not value, just return false. Output was 2. I don't think I'm checking for the valid value correctly. If row is less than equal to 0, less than 0, for row is greater than grid length, or call is less than 0, or call is greater than grid sub. So grid, so at this point, grow does exist, so the grid then return false. We just want to stop. So this only runs, this is running twice. And it should be running once. There seems to be a slew of ones and I'm missing. These ones here should all be 0. I need these all to run actually, because once I run into one that's true, then I return true. I think the thing is that if grid equals 1, it should just be islands plus equal 1, and we just do find island. To clean up, or I should say clean up nearby islands. That way we don't even have to return anything. Oof. Oh my god. Okay, so the call stack is too large. Maximum call stack exceeded. Surrounded by water. You have to check in 4 directions though. Maybe the goal is to iterate over all of them. Damn, we got close, but Call stack size exceeded. That's the executed input. It's not even that big. Calling the function 4 times only when it equals 1. Or, you know, you could always just change it to 0. Well, I should be reusing my answer here, so I'm not understanding why. Maximum call stack size exceeded. Now we have to duplicate it, or we could just reuse it. We reuse it. Treat the 2D grip map as an undirected graph. There's an edge between two horizontally, vertically adjacent nodes of value 1. Treat the 2D grip union find. Looks like most of these are graph dependent. So treat the 2D grid map. I guess that's technically what I'm doing, since what I'm doing is a I'm doing it in all 4 directions. Linearly scan the 2D grid map. If a node contains a 1, then it is a root node that triggers a depth first search. That's what I'm doing. During depth first search, every visited node should be set as 0 to mark as a visited node. Count the number of root nodes that triggered DFS. This number would be the number of islands since each DFS starting at some root node identifies an island. True. So code is messed up here. Yeah, I think I was so close, but I think the way I was going about it was just running out of space for some reason. So the way they did it in Java, this BFS. R minus 1 is greater than or equal to 0. So I'm triggering a depth first search on every call. They're only triggering a depth first search if a node equals 1. Well, we have the same start. If RC equals 1, plus no minus DFS grid RC. So they kick it off. But they also do the same internal check. It's actually this very similar code. It's kind of crazy. Find island. So it's, but I'm already checking for that up here, so I'm not understanding if I'm out of the bounds at all. Row is less than. Oh, I'm checking if the current row is out of bounds. Yeah, that makes sense. Error then return. Let me see someone else's submissions. Yeah, I think I'm just gonna call it there. GG.